Okay, now we get into the inverter driven, which is kind of the question, or the inverter creates all the questions that drive me a little crazy. So here is just a standard inverter waveform, again, in our software, where we have a PWM voltage line-to-line measurement, a relatively low switching frequency, and we can see that current ripple affecting that. You know, that the current has a really nice ripple to it, the voltage has those square waves, and I think you can imagine that if we multiply voltage times current, we get a pretty interesting power output. So fortunately, the motor acts as a filter to remove most of these harmonics from what we see at the shaft output. But this is actually a different example because it's a better example. If we take voltage, which here is in blue, inverter driven, times current in red, which you can see is pretty smooth. It's got some probably like fifth harmonic in there. And then we look at our power. That power is happening at the switching frequency. That power is oscillating at the switching frequency. Now, when we average the power, we get a really nice average. You know, we get something like a 2.4 kilowatt average. It's very nice. But we have that really high frequency in the power. So if we look at the calculations, and this is based on, I think it was a 200 kilosample sample rate, or maybe it was actually no, this would have been a 200 kilohertz filter rate, so 500 kilosample sample rate. Our phase angle, again, this is of the fundamentals, because that's really the only way to calculate it, is 5.9, so relatively low phase angle. But our power factor is 0.311, because this is power factor calculated with all those harmonics. Power factor of the fundamental is 0.998. So what's the difference here? And the difference is switching frequency. And now we have the real power, which is the total power measured output, 2.27. And the fundamental power is 2.26. So, you know, there's a couple of, or 12 watts, 13 watts difference in the power. So there's not a lot of difference. It's very, very small, but there is a difference. So again, we need to, my fundamental has this much power, my total has that much power. There's a difference. So let's dig into this a little bit. So full sample rate calculations, 50 kilohertz, no filter. Apologize, I had it written down. And we see our voltage has this, you know, again, the high frequency inverter. Our current has a little ripple to it, but relatively sinusoidal. Our power has those high harmonics. And if we run through and do all our calculations, you know, S equals IRMS times VRMS, Q equals S squared minus P squared, we get the given values you see. You know, 69 volts, 104 amps, you know, 2.27 kilowatts, but absolutely huge apparent power and reactive power. You know, we can see that we've got 7.9K VAR or VA and 6.9 VAR, low power factor for a relatively small phase angle. Now, if we look at a 10 kilohertz filter applied, so we apply a 10 kilohertz filter to voltage and current, so they have the same phase distortion. VRMS now goes from 69 volts RMS to 23 volts RMS. This is just by applying a 10 kilohertz filter. Now, I think what I didn't mention is that this is a 20 kilohertz switching frequency. So we're now taking that switching frequency out of the RMS equation, because again, we're just inputting it into a math engine. The math is doing what it does. We need to know what we're inputting. IRMS is relatively the same because it didn't change much. There wasn't a whole lot of inverter effect because the motor is a good filter. Power, pretty much the same. Reactive power and apparent power drops by 200%. Reactive power drops by 6x. The power factor comes to 0.899. And we actually, the phase angle is improved as well because we take a lot of the harmonic content out. Now let's look at the fundamental, and we compare the 50 kilohertz, the 10 kilohertz, and the fundamental. And what we find is that 69 volts goes down to 21. So there is still a difference between the, we filtered out the switching frequency and the fundamental. And this is those fundamental-based harmonics. This is your 5th, your 7th, your 13th, your 11th. So again, we need to ask ourselves, where do we want that filter to get our RMS values? Or do we just want to operate with fundamental? Call it a baseline. IRMS, now we get a difference. 104.03, 104.03, 103.84. We've eliminated the switching, but now we're eliminating, again, those fundamental-based harmonics. So those rotational-based harmonics now. Power, there must be a little bit of 5th or something, because P fundamental is, again, a little bit higher than P average and P filtered. Apparent power, and now reactive power is the big one. We go from 6.8K to 113 volts amps reactive. Also our power factor, 0.309 to 0.998. These are big differences just based on filtering. How many harmonics of the fundamental do you want in these calculations? That's the question. And I lay it out on a nice little table, and the questions are valid when people say, why is my measurement on one instrument different from another? Why is my MATLAB calculation different than my instrument? You have to, why is my scope different than my power analyzer? By like really drastic sums. Well, you have to ask yourself, what are you filtering at? Why is my model different? Well, what filter does your model have in it? How ideal is it? So this is the big question that I pose to people is, what are the filters? What bandwidth do you want to understand in these calculations? Because I can't give you the right answer. I can tell you why you're getting what you're getting. And I also think it's very interesting to see that it can affect power. This is only, 10 watts of difference, but 10 watts of difference is pretty significant. I'm going to skip it over the sales pitch. HBK sells instrumentation for measuring power. We have a lot of tools to help you analyze this stuff. You can take that offline with me if you like. In conclusion, reactive power and RMS are complex beasts. So please consider what values you want to look at, and really consider that before you acquire data. I'm of the stance that take it as high as eliminates anti-aliasing. So, if you're switching frequencies at 10 kilohertz, measure at, 500 kilohertz and, filter at 200 kilohertz, eliminate all that electrical EMC, EMI noise, and then you can filter afterwards. But, do what's right for your test. I come from the particularly nerdy world. Make sure you're comparing apples to apples. Even if you have a variety of instruments, just make sure your filters are consistent. You're getting the same harmonic bandwidth. If you're measuring things with scopes or you're measuring things with your internal system, make sure your instrument matches your internal system. High frequencies cause reactive power, and whether it's real or not, the math gives you values. So, we can have a debate all day if it's real or not, but the math gives you these values that we need to account for when we're doing these calculations. HBK gives you equipment and expertise to help do these. And I would like to thank everybody and open up the floor for some questions.